You know, when we think of Einstein's general relativity, we picture this perfect, untouchable pillar of modern physics. But what if I told you that deep inside its very foundation, there's a crack, a really deep philosophical argument that kicked off the moment it was published and is still going on today? Let's explore this fascinating flaw right at the heart of it all.
So check out this quote from a paper that really frames our entire discussion. The core idea that Einstein himself called his fundamental principle, well, it was immediately attacked for being physically vacuous. That's the polite scientific way of saying his masterpiece was completely meaningless.
And that's the big question, isn't it? How on earth could the key that unlocks general relativity, a theory that's been proven right for over 100 years, be called empty? To figure that out, we've got to go back to the very beginning.
All right, let's set the stage for what is, honestly, an incredible intellectual drama. This is a foundational fight that has been shadowing Einstein's greatest achievement for more than a century.
This whole story is laid out brilliantly in a 1993 paper by the physicist and philosopher John Norton. He basically chronicles how this central pillar of Einstein's thinking was challenged right from the get-go. And what's so wild is that this isn't some obscure academic squabble. It cuts to the very heart of what general relativity even is.
We all know the triumphant story, right? It's 1915, and Einstein drops his general theory of relativity on the world. It completely rewrites our understanding of gravity, of space, of time itself. It predicts gravitational waves, black holes. It is an absolute triumph.
But buried inside this masterpiece was this one concept that even Einstein himself really struggled with. It was a principle he thought was the key to the whole universe, but one that his critics would just brush off as a mathematical trick.
So, what was this big controversial idea? Well, it was a dream of ultimate universality, an idea he called general covariance.
Okay, let's back up for a second. With his special theory of relativity back in 1905, Einstein gave us this really powerful idea. Whether you're standing perfectly still or cruising on a smoothly moving train, the laws of physics look exactly the same to you. As long as your motion is steady, the rules of the universe don't change.
And he had the math to prove it. It was called Lorentz covariance, which is just a fancy way of saying he had a mathematical guarantee that the laws of physics would hold true for anyone moving at a constant speed. It was beautiful, elegant, and it just worked.
And listen, this wasn't some minor point for him. As he said back in 1910, he was convinced that all natural laws had to play by this rule. For Einstein, covariance was everything. It was the language of reality itself.
But just steady motion, that was too limiting. Einstein had a much bigger dream. He wanted a principle that worked for any kind of motion, speeding up, slowing down, spinning around, tumbling through space. He believed the laws of physics had to be truly universal, for everyone, everywhere. And this was his grand quest for general covariance.
But this amazing ambition led Einstein straight into a trap, a terrifying logical paradox that he himself created, and it would cost him nearly 3 years of his life.
You know, Einstein's superpower was the thought experiment. But this one time, it totally backfired. He came up with a scenario that seemed to prove his entire project was completely doomed from the start. It's famously known as the hole argument.
Okay, let's walk through this. First, just picture a patch of space-time that's totally empty. No matter, no energy, nothing. A hole. Now, logic says that the physics happening outside that hole should perfectly predict what the gravitational field is inside it. There should only be one answer. But when Einstein applied his generally covariant equations, it was a disaster. They didn't give him one answer, they gave him infinite answers. This meant his beautiful principle led to a total breakdown of causality. The laws of physics couldn't predict the future anymore.
So he gave up. This is the crucial point. For almost 3 years, from late 1912 to late 1915, Einstein was convinced that general covariance, his guiding light, was a huge mistake. He was actively working on theories that were not generally covariant, all because of this ghost he'd found in his own machine. But then, in the final, frantic weeks of 1915, he saw his way out. And he didn't do it by changing the math. He did it by changing the meaning of reality itself. His escape hatch was this new idea, what we now call the point coincidence argument. He realized the mistake wasn't in the equations at all. It was in his assumptions about what the equations were even describing. He'd been thinking about space-time as this fixed background, kind of like a piece of graph paper.
But he had a breakthrough. He realized that the graph paper of space-time, that's not what's physically real. As he put it, the only things we can ever actually observe are meetings, the intersection of a planet and a beam of light, or two particles colliding. These coincidences are the real stuff of physics, not the abstract coordinates we draw on our imaginary graph paper.
So the solution was just brilliant. Those infinite possibilities inside the hole, they weren't different physical realities. They were just different mathematical descriptions, like stretching or warping the graph paper for the exact same physical situation. The breakdown of causality was an illusion. Einstein had beaten his own paradox, and general covariance was back on top.
But just as Einstein solved his own internal crisis, an external one was just beginning. In 1917, a physicist named Erich Kretschmann came along and argued that Einstein's profound, beautiful principle was, well, nothing. He claimed that if you were clever enough with the math, you could rewrite any theory to be generally covariant. He said it wasn't some deep principle about nature, it was just a choice of mathematical language. In his words, it was physically vacuous.
And that, right there, set the stage for a debate that has simmered for over 100 years. A really fundamental disagreement about what Einstein's masterpiece is actually telling us about our world.
And as you can see from this timeline, the argument never really died. After Kretschmann fired that first shot in 1917, things cooled down for a few decades. But then a huge renaissance in relativity research in the 1960s brought it all roaring back to life. Is general covariance a profound physical principle, or is it just a mathematical choice? The disagreement is still very much alive today.
So we're left with this absolutely fascinating question. Was Einstein right? Did he find a deep fundamental truth about the universe, that the laws of physics are truly independent of how we look at them? Or were his critics right all along, that he'd simply found a clever feature of our mathematical language? The question still hangs there. If the laws of nature look the same no matter how we describe them, what does that tell us about reality itself? That's the crack in the pillar, the argument still echoing in the heart of relativity.